of conditional signal assignment. One is so-called if-then statements. Another part is case statement. So we'll try to figure out how such sentences, such assignment sentences, look in VHDL FPGA programming. All right. So. I'll share my slides. Okay. All right. So today we're going to talk about the conditional signal assignments, and one moment, we have discussed it basically along the wrong slide. It's no, not this one. Sorry. So I've already spoken last time that if we're talking about the logic and the structure of our source code, there are two kinds of source code. It's the so-called concurrent part or combinational logic part, and another part is sequential part. So in sequential part, each procedure is executed one by one. If we're talking about the concurrent part, all the assignments are accomplished at the same time. So like they work in parallel. All right, so what are we going to talk about today? First of all, we'll talk about the simple signal assignment. So simple signal assignment is the way when we assign a signal with a certain value, another or certain expression. Another part is conditional signal assignment, which corresponds to the if-then statements. Another part is selected signal assignment, which corresponds for case statements in conventional programming, and will compare conditional and versus selected signal assignment. All right, so the simple signal assignment. In the simple signal assignment, for example, we have a certain signal and we want to assign it with a certain value. We just use arrow and equal, and arrow specifies the direction of assignment. So the signal called signal name is assigned with certain projected waveform. And how does it look like? For example, y is equal a plus b plus 1, and it will implement this assignment after 10 nanoseconds. All right, so and timing could be also ignored if we don't specify any particular timing. It could be very useful for modeling. And now let's continue with a simple signal assignment statement. What you have to know that in one assignment you first of all you can assign a certain value. Another way, if you don't want to assign a certain value but you want to assign a certain expression, like in this case we have 3 adders and 1 subtractor in series connected to achieve certain result, like a plus b plus c minus 1. And you have also to remember about using brackets, that we already have discussed this the last lecture, that there is a certain execution order also in VHDL. Therefore, if you want to change the order or if you want to make your code more readable, you could add additional brackets to specify the sequence. But by sequence, I mean that it will depend in which part of your electrical circuit does this operator exist. All right, now let's start with the conditional signal assignment. Conditional signal assignment, it means that you have a certain condition for assignment of value. So it consists of value expression and Boolean expression. So it's a condition, in other words. So this looks like that. You want to assign the signal with a certain value. Interesting. All right, so you want to assign the signal with first value expression. When, so this is your condition, you will assign the signal with value expression number 1 when this Boolean expression is true. If this expression is false, so return 0 is false, is not true, then you continue to the next expression, and then you once again check the Boolean expression. So value expression 2 is assigned when Boolean expression is 2 is correct. Otherwise, you continue until the last one, and you have to remember that the last expression has to be assigned without any conditions. Otherwise, the memory will be generated, which will cover a huge amount of your chip, of your FPGA, and you don't need memory in this case. So it will be wrong. All right, let's continue. So for better understanding, I'll try to explain the source codes of four different circuits, and we'll try to map all our source code into a physical electrical circuit. How does it look like in your FPGA board? So we'll start with the multiplexer 4 to 1, and we'll continue from there. Now I'll try to show everything in one screen for you to see the truth tables. A moment. All right, now I think you should be able to see both parts. Now I'll share the whole screen once again. All right, now you can see the truth table of our mux, and on the left side you'll be able to see the source code. Do you see it like that? Can you see the truth table on the right and the source code on the left at the moment?
Yes, Professor.
All right, that's good. So here we have, first of all, according to our truth table, we have to specify the entity. Our entity port is the way how our program communicates with the outside world. Yeah? So in this case, what does the multiplexer? Depending on the addressing input, which is our control input, depending on the value of addressing input, our multiplexer connects any of the preferred input, A, B, C, or D, to our output X. To make it more logical, all our inputs A, B, C, D, and output X are 7-bit, are 8-bit 1-byte signals. So we have it. A, B, C, and D are inputs of STG logic vector 7 down to 0. Like we already have discussed the last time, that we are using STD logic signals to communicate to the outside, because it's the they can have 9 different values, so they are very suitable for modeling, and also they have Z state, which corresponds for high impedance state, like an input and so on. So therefore, always our input and output signals communicating outside of the board will be the type of STD logic, or if it's an array of STD logic, in this case it would be STD logic vector. All right, so this time we have 8 bits, so 1-byte input signals. S is our also input, is a control signal. As we can see, it's a 2-bit control signal, so it's STD logic vector 1 down to 0. And X is our output, which is also the same type like STD logic vector, like all 4 our inputs. So now we have to specify the architecture for this multiplexer. In this case, what do we do? Conditional architecture of multiplexer is, and what do we have? X is assigned with value A, like you can see, when certain condition, our select signal or control signal is equal to 0, 0. Yeah, you can see 0, 0. B, when S equals to 0, 1. C, when 0, 1. And all other cases, D. What is important, you cannot write D when S equals to 1, 1. Why? Now I'll explain why. Because if you write 1, 1, you will only specify 4 values. Actually, the signal of STD logic can have 9 values. So at all, there are 9 multiplied by 9 is 81 conditions. So in total, we have 81 conditions. But in this case, we would specify only 4 of them. So 77 conditions are left unspecified, and your synthesizer won't understand what value should it obtain at those conditions, as they are not specified in any way. For this case, as your synthesizer doesn't know what to do, it will probably generate a memory to store those values. So what we have to do to avoid this? There are 2 possible ways. The first way is doing it like this. When you don't specify a condition for D, as you know that in real life, your signal can achieve only value 0 and 1, and other ones are for modeling. So probably it won't achieve any values in a real board. Or you could add additional signal, and else you don't care. But we'll stick to the syntaxes, and we'll write the conditional signal assignment this way. All right. The next part is the binary decoder. All right. I'll shift here to binary decoder. Here it is. All right. So binary decoder decodes code of position 0. We have an output of 1 at the last position. 0, 1 is 1, 0. The 1 is in the in the third place, then in the second, and here you have one in the highest bit. So we decode from 2 bits to 4-bit signal. So how will it look like? So first of all, it's easy to understand that entity will consist of 2-bit input and 4-bit output. Yeah, we can see that both are STD logic. This one is 2-bit, this one is 4-bit. All right, let's.
So, Professor, please, I need to make sure that, so now during the lecture, you are going to explain like the syntax of the VDHL language, right?
In some way, yes.
And in the other ways?
Because we're not going to talk only about the syntaxes. When we're going to talk, I think in 2 lectures about the memories, we'll stick to the same syntaxes, but we'll try to code completely different things. We'll try to code memories, to code flip-flops and latches ourselves. So this means that we won't talk about the syntaxes, but we'll talk more about the structure.
Like the algorithm.
The algorithms, yes. We'll talk more about the algorithms, how to code and understand what you're coding with HDL.
And during the laboratory works, we will just like implement the algorithms and syntax we took during the lecture, right?
Not exactly, because you know that as we don't have physical laboratory works, so we'll cover just we're going to, I already explained that, I think, first lecture, but we'll cover all the course, and I won't split it to laboratory works and to lectures. We'll try to go through some code, through some theoretical part, and then you'll have some practical tasks. And once again, because I'm not going to mark whenever you participated or did not participate at the laboratory works, but if you won't participate laboratory works, you won't get enough knowledge to accomplish your tasks.
Yes, I understand. I'm just like trying to understand if you're gonna separate like the.
No, I'm not going to. I'm not going to separate. It will depend on how it's going to work with you. As you know, it's the first time we're working not directly through Zoom, so I'm not sure how will it go with modeling on your side. So I'm not sure on the amount of material we'll have. So at the moment, I cannot exactly tell you how will it be split.
And if I want the next like help with the program with the program or the IDE for the first time, should it be during the lecture, or I can email you and take like an other time, because I just got the program settled yesterday, and it was like but I didn't know how to use it still. So
right, so it's always like this. If you have any particular questions on VHDL, on some coding, you could write me an email and we could arrange a Zoom meeting and discuss the problem. That's okay. And maybe with some particular tasks, we'll agree that you have the time until some day to upload the source files. If we agree on timing together with you, then there will be a certain timing for upload. But like this task, it was just for you to practice. So if you did not stand or didn't manage to do something, that's, well, you just won't get enough knowledge, but it's, you know, it's your choice.
Okay, thank you. No, but I won't give it up. I'm just like, I just got late by installing the program because we had issues because the program is an old version and it's hard to install it on the new laptops or in Windows 10 in general.
Yeah,
so that's why I was late.
So don't worry about that. When we'll agree about the accomplishing task in certain time, I will explicitly explain that we have time until certain day, and you have to upload it to Moodle. So you each time, if you need to do any particular task and to upload it somewhere, there will be a place in Moodle for uploading, for you to know the exact date of timing.
Okay, thank you very much, Professor.
Okay, you're welcome. All right, so now we could continue back to our binary decoder. So it's easy to understand that input is a 2-bit and output is a 4-bit, as we can see from the truth table. So how should it be coded? If we are using conditional signal assignment, so again we have an architecture, and the output will gain value of 0, 0, 0, 1, when control signal is 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, when control signal is 1, 0, and at all other cases it will be 1 in the highest bit and 0, 0, 0. What is important to understand that in both cases, in the case here, like we see of a binary decoder, and in the case of multiplexer, there is absolutely no priority of condition of checking the Boolean condition. So you don't care whenever you start checking the condition from this side or checking the condition from downside upwards. This means that all the conditions don't depend on the priority you check them. But the conditional signal assignment itself is prioritized, and it has priorities. It will start, like in this case, you can see that it starts checking from the first condition, from the top one. So this means that it arranges the circuit in series, and it starts checking from the highest priority condition. So what do we get here? In these both tasks, in the multiplexer and the binary decoder, we overspecify the code, as we don't need the priority, but we still implement it. So we'll talk about it a little bit later. But for these two tasks, particularly, the selected signal assignment is a better match, as it doesn't imply unnecessary priority network. So in other words, you add additional information which is not implemented in any way. Now we're going to talk about the priority encoder, and with the priority encoder, for the priority encoder, the priority already is important. All right. Now we have the truth table here. So for the priority encoder, what happens first? First of all, you check the top bit, the highest bit, and you don't care about all the others. This means that, for example, if we have the number of 1, 1, 1, 1, and we'll start checking from the other side, we'll get completely different meaning. You see, if we'll start checking bit by bit from another part, and the 1 is in the lowest section, we'll get completely different code. So for priority encoder, it's important to root the priority of execution. And we see that if the highest bit is 1, then code is 1, 1. If highest bit is 0, then we check another bit. If this one is 0, then we check once again another bit. If this one is 0, we check another bit. And if all bits are equal to 0, not only code is 0, but also there is no bit active, which implies that there is no ones in our input. So once again, like here in priority encoder, we'll try to write a code. It's a nice in VHDL that we can access bits of our inputs directly by writing the bit number in brackets. So how do we do it? First of all, our port entity is our input is 4-bit input. We have it. It's the logic vector 3 down to 0. The code output is a 2-bit, and again, active is single STD logic output. Okay, so how does it look like? As I've already mentioned, here we start with the priority. First of all, we check for the code 1, 1. So we start to check the first Boolean expression, the highest priority for the highest priority Boolean expression. So we start from the highest bit. So third bit, if the third bit is equal to 1, then the output is 1, 1. Then else, if not, we check for another condition. If the second bit is 1, if that's true, then we check for the first bit, and at all other cases, the output is 0, 0. All right, and the active, our active signal is just logical OR functions of all four bits. Right. Okay. Now for the simple arithmetical logical unit. Simple ALU. For the simple ALU, we'll try to build a simple arithmetical logical unit. So our inputs. We're going to work with two inputs, source 0 and source 1, which all are 8-bit signals, so 1 byte. Our result is our output of our mathematical operation, and it's also 8-bit, and also a 3-bit control signal. If the control signal is 0, then we increment source 0 by 1. We add 1. In all our cases, we calculate the sum, the difference, logical AND, and logical OR. So at all, our simple arithmetical unit can execute 5 different functions. So first of all, like always, we'll start with entity. So entity of simple arithmetical logical unit is control signal is input of 3 bits. Our two inputs, source 0 and source 1, which are 8-bit, so 1 byte, and our result and output. And how does it work? Well, to make it easier, we can start from employing free redundant signals for calculating intermediate values. So we'll start with incremented value. So we'll build a circuit for calculation of the increment. So first of all, we have sum, and we calculate and addition and subtraction at the same time. So for that case, we are using signed, as when we subtract, it's pretty plausible to get negative values. So we are, first of all, we cast our source 0 signal into signed, then add 1, and when we get the mathematical expression, we cast it back to std logic vector. For sum, we cast source 0 to signed and source 1 to signed, and then we calculate the sum and cast it back to std logic vector. For difference to subtract, first of all, we cast them both again into signed, calculate the difference, subtract one from another, and then cast the result back into std logic vector. All right, how does it look like? Now the conditional signal assignment, so the machine of our simple arithmetical logical unit. So the result will be assigned with the value increment, this one, incremented by 1, if the top, the second, or the highest control signal bit is equal to 0. As we can see here from the table, if it's equal to 0, the incremented value is assigned. And else, in other cases, we'll check the lower 2 bits of our control signal, only these two. We don't care about this one anymore, as we have already checked it in previous condition. So for our ways, it's equal to sum when 0, 0, to difference when 0, 1, and we directly execute logical AND when 0, 1, and in all other cases, it's OR. All right, it's less than a minute left, so let's reconnect to Zoom. All right. All right, so I'm waiting for you to reconnect. All right. Well, it is like it is. About the source code you can see now, so I can answer you right now. After the lecture, I will add the slides of today's lectures to the Moodle, and it will be accessible all the time, because you'll need it. You have to understand that VHDL is a pretty complex programming language, so you definitely will need this source code. And I hope that you will write a lot more source codes during our practice, and tomorrow we'll try to I hope that everybody will manage in installing the software. I will also work with VirtualBox, and I hope that everyone will manage installing software and will be able to accomplish the second laboratory work. All right. Okay, so let's continue. Okay. All right. So with a simple arithmetical unit, you remember, yeah, that in last executed part is logical OR between source 0 and source 1. You have to understand that for logical AND and logical OR, we don't need any casting or conversion, as it's a bitwise operation executed directly with STD logic vector input signals. Okay, let's continue. So hardware of conditional signal assignment. We have to understand, as I already told you, that it consists of three different parts. First of all is value expression circuits. Here we have value expression. It could be a certain complex value expression you want to assign. Then Boolean expression circuits. So these are Boolean expression circuits for the conditions. And the last part is a priority routing network, which enumerates the exact priority of each Boolean expression. So this means as it's a combinational part and it's executed at the same time, the only we are not able to split the operators in time, and the only part we can precise it is arrange the circuit in series. And now we'll see how does your real circuit look. So we could express each condition checking statement as a multiplexer 2 to 1. Yeah. So we have an if statement, some certain Boolean expression, and if it's true, then the output signal is assigned with the value of first input. If it's false, it's assigned with another expression. So it's easy to understand. But what happens? So what does it look like? Value expression 1, value expression 2. And here we go with the Boolean expression. So and our signal here. So signal is assigned with value expression 1 when Boolean expression 1 is true, and is assigned with value expression 2 when Boolean expression is false, in this case. Easy. What happens if we have a more complex conditional signal assignment? If we have more complex conditional signal assignment, each new Boolean expression is a series branch of our circuit. So how does it look like? First of all, the top one, we always start with the expression of the highest priority. So first of all, Boolean expression number 1. So if the Boolean expression number 1 is true, we assign the signal with value of value expression 1. Else, if it's false, we continue to another part. But if it's true, our circuit is connected directly to signal and assign, and this part of the circuit remains not connected and has no impact on our output. Then, if value expression 1 is false, then we check for Boolean expression number 2. So if the Boolean expression number 2 is true, we assign the signal like this, prove this true and prove it's false, like a wire to the signal. We assign the signal with value expression 2. Once again, if the Boolean expression 2 is false, we continue to the third one, and we check for the third Boolean expression. If it's true, we assign the signal with value expression number 3. If not, we assign the signal with value expression number 4. And that's it for this case. So the more Boolean expression we have, the longer the series circuit becomes. Well, I hope it's pretty clear for you. All right, and now conditional signal assignment, actual implementation. Well, you remember probably from logical circuits or from digital circuits that you could you could build any circuit from logical elements. And here you see a 2-to-1 multiplexer built from one negation, two AND, and one OR logical element. Right. Also, we can add certain expression like here to our Boolean expression. So here we compare A and B. If A sorry. All right. So if A equals B, then the Boolean expression is true. So we can already add a certain mathematical expression into our Boolean expression. And here you can see that using Carnot diagrams, we can simplify our circuit. For example, from this one to simple XOR. What else you should take in mind is understanding of optimization level. Well, it depends on synthesizer quality, how much can it be simplified in it, your circuit. Another part that we have to understand that there could be more involved. You can have more operators, for example, A plus B, A minus B, and so on. In this case, here we have adder, here we have a subtractor, once again adder, and here additional more, not equal, and so on, additional value expressions which are employed. And you can also connect certain value expression as a Boolean expression. All right. So let's finish with the complexity. Now we'll talk about the selected signal assignment. So in this case, what's important? Selected signal assignment has the main severe difference is that it has no priority network. So in selected signal assignment is like in case statement. All the expressions and all the Boolean expressions have absolutely the same priority. So they are not prioritized in any way. So in certain cases, when you don't need priority, it means you don't over specify the circuit. But if you need priority, it becomes a little bit more complicated. Like you cannot use priority. So this means we have to use certain rule. All the chases must be mutually exclusive and all inclusive. This means that you have to specify all possible choices. You cannot leave one unspecified. In this way, synthesizer will generate fault. And also, you are not allowed to use unclear choices. All choice must be exclusive. So there cannot be choices which are the same in any way. So how does it look like? First of all, this assignment sentence starts with word with. So with select expression. So this is your expression on which depends your selection. Select. So depending on select expression, select signal with signal a value. And now value expression 1, 2, and so on when certain choice. So naturally, we have the question, what should we do for the last choice, as we have to specify all the choices. So the last choice will always end with others. So we enumerate all the choices and expression certain, the last one when other. So at all other values. So now we'll start again with the multiplexer 4-to-1. Here on the right side, I will once again show you the expressions, the truth tables, and we'll work on the same sort on the source codes for the same for circuits. So first of all, we'll start the same way like with the conditional signal assignment with the max 4-to-1 multiplexer. All right, so entity is the same. And now how does the selected signal assignment statement look like? So with S, certain our input control signal with S expression select A, X is equal to A when 0, 0, B when 0, 1, C when 1, 0, and D when all other cases. Only take notice that we are using comma. All these values are comma separated, as you can see. So it's a little bit different syntaxes. We have to add comma. So not semicolon like in other cases. All right, let's continue to our binary decoder. All right, for binary decoder. So for binary decoder, once again, we have input of 2 bits and output of 4 bits. How will it work? So once again, with certain expression as select, the outputs for x, and x is equal 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 1, 0, 1, according to a truth table, and 1, 0, 0, 0, when 1, 1, 0, and 1, 0, 0, 0, when all the other expressions. So for now, it was pretty easy to understand. It was very, very clearly and very common and close to the conditional signal assignment. Now, the interesting part happens when we're talking about prioritized signal assignment. And as I already have told you, first of all, there are no priority routing network. The second part, all our signals should be mutually exclusive. So what happens? In this case, we have to enumerate all possible values, because if we'll write only the condition for this bit, you can see that it could be gained with a lot of different combinations of our control signal. So if we'll check only for one bit, it will not be mutually exclusive, and if we will not enumerate all of them, it will be not all inclusive. So in this case, this strip means or, logical or among all these conditions. So if any of these conditions is Boolean conditions are true, then we have our code equal to 0, 1. So if the highest bit, the top bit is equal to 1, there are in total 8 possible combinations of left 3 bits. So we have to enumerate all 8 of them. When we check for 0, 1, here we have 2 places, so 4 possible combinations, and here 2, 1 either 0, and we have to enumerate them all. And the last one covers 0, 0 when others, and active bit is calculated at the same time. Now it could in this case we are not allowed to use it as the conditional assignment statement is not mutually exclusive. There could be an idea that you could write like this, that don't care, but the signal value is don't care. But this won't work and will always return you 0, 0, as in real life, your input signal cannot get value of don't care. It's always 0 or 1 or Z, and that's all. It never takes the value of don't care unless it's specified so in modeling. So it won't work, and it will work only in modeling if you will on purpose specify the signal value don't care. In other cases, this will return 0, 0. So once again, this execution will be wrong. All right, simple arithmetic and logical unit. For simple arithmetic and logical unit, what we're going to talk about. The entity is the same, and our intermediate signals are also the same. And here they are calculated. Now, how we are going to prioritize them? So the only one which has several possibilities is increment, because it could occur under under 4 different our control signal values. So we have to enumerate all 4 of them, and if they're true, our result is equal to increment. All other values are already mutually exclusive, so we just write them down. Okay, now let's do it like this. All right, so now the interesting part is to see how does it look like, how does the real circuit look like in this case. Well, here is a short mention of how it could be implemented. Also, for example, selected signal assignment is very convenient for truth tables. So in this case, we have truth table of 4 elements. But for example, we'd like to use some more specific function. For sure, for 2 bits, it's very easy. But if we're talking about 3 bits and so on, it becomes more complicated, and there are we could use some certain specific truth tables or some specific functions. So we could write down all possible values. So for example, we could imagine that we have input signal and A and B of 1 bit and 1 bit output, and our synthesizer doesn't have pre-built OR function. So how would we do it? First of all, we're going to use the concentrate operator to concentrate A and B into signal TMP of 2 bits. So concentrate and bring 2 bits. And now we check, we've selected signal assignment, all the conditions. So the output is 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, and all others also 1. So here we wrote down the truth table of OR element, not employing the pre-built OR function. So if we have more sophisticated function, we could also build its truth table employing selected signal assignment. So how does it look in real life? So in this case, it's a single multiplexer with a certain amount of outputs depending on the select signal, on the width of select signal. How many control bits does it have in it? So if we have a signal, if we have, for example, 2, if we check for 2 values, it will look like this. We have certain control signal, and we have a parallel multiplexer, value expression, value expression, value expression. So in this case, we are going to employ the multiplexer 4 to 1. So we have a select signal, a 2-bit select signal, and with a 2-bit select signal, here is all our choices. If we have 3-bit select signal, once again we have more choices. If not all of those choices specified, we'll connect them like this using others. All will be connected in parallel. As you can see, in this circuit there is no priority routing anymore. And here's how such multiplexer can be built from logical elements. Also, we can employ additional mathematical circuits into our combinational circuit. All right. Also, we can have several Boolean expressions mentioned in each one. Now, how could we convert from one side to another? So it's always easier to convert from the selected signal assignment to conditional signal assignment, as conditional signal assignment has priority routing and selected signal assignment doesn't have priority routing. So if we have more parameters, it's always easier to convert it. Just take all the values and just assign signal with value expression 0, 1, and write down all the conditions. Cell is equal to C0. Again, value expression number 1, and you enumerate all using OR logical function. You enumerate all Boolean expressions. So in this case, it's easy. If we're going to assign in opposite way, it gets a little more work to do, and we want to keep and we want to enumerate on values to make it mutually exclusive, and to write the same source code in not employing the priority networking. So how will it look like? First of all, one of the easiest, dependent on three Boolean expressions. So certain select signal, Boolean expression. So we have 3 Boolean expressions, and each bit of our select signal is equal is assigned with Boolean expression value. So select 2 is 1 when Boolean expression 0 is true, else, and so on. So we assign 3 bits of our select signal, and now the only part what we have to do is to enumerate them properly. So depending on the priority of our conditional signal assignments, we'll add additional enumerated values depending on its priority. For example, if Boolean expression, this one is the highest priority, we would add certain signals, certain conditions here, not here. But as this one is the top priority, so we enumerate all those values for value expression 0. All right. So that's probably it for today. All the theory. What I wanted to tell you. We'll do it like this. As we still have some problems with Model Sim. Today I'm going to work on VirtualBox and Module Sim install. And for today's lecture, I also will add some personal task for you all to Moodle, just to practice. You will have to model certain source code to understand what we were talking about. I think I'll add it tomorrow, so after tomorrow's lecture. And for tomorrow, I'm going to prepare and to try to find out how to install the software in VirtualBox. So that's probably it for today. Do you have any questions? All right, so tomorrow we'll meet at our time. So see you tomorrow. All right, bye.